So maybe I'll start off by, well, in the past two lectures we learned about special relativity and general relativity, right? And so basically the sort of flow of this class up till now has been, we learned about classical mechanics, and then we learned about E&M, and then we sort of learned that classical mechanics is not quite the full story. There are space and time are not exactly how we understand them in just classical mechanics. So today we're going to learn about a type of physics in which classical mechanics is essentially true. It doesn't have, like, this also applies if you include special relativity or general relativity, but basically we're going to be using classical mechanics. There's no real new physics in thermodynamics, but the one thing that is new in this case, and I think what is the big idea of thermodynamics, is that it's basically it's basic physics, except where you don't know everything. So what do I mean by that? Let's say you have a box, and you have particles moving around in the box. Basically random motion of particles. And this system is super complicated. Like if you have atoms of a gas in a box, there could be trillions of atoms in this box. And each of them has their own velocity in its own direction, and it's bouncing off objects. The system is super complicated. Super complicated. And in a very real sense, it's chaotic, right? If you even change the position of a few of these particles, maybe even one of these particles in the box, and you fast forward the system, you're going to find out that the individual motions of all of the different atoms in this box is going to be completely different. And remember, that's the definition of chaos, right? Slight change to the initial parameters of a system changes the end result dramatically. So this is chaotic, and so what we could do is we could just sit here and count up the velocities of each of these particles, record them down, and try to predict the behavior of the system in the future. But who's going to sit here and do that forever? That's unnecessary. And it's also impossible. So what we do in thermodynamics is we sort of accept that we're never going to know the individual velocity of every single particle. And instead, we ask, what can we predict about how this will behave? What will we be able to see about this system on a macro scale? What emergent behaviors come out of this system when we don't know the specific velocities and energies and things about every single particle in this box? And that's basically the essence of thermodynamics in my opinion. So fine, we have this system. Just like in classical mechanics, there are certain laws of thermodynamics. And I'm going to basically list out the laws. And just like we did for classical mechanics with Newton's laws, just keep in mind that these laws are not like because of like some law of physics. These are all things that come out of just putting a bunch of atoms in a box, letting them move about, not knowing how the specific atoms are moving. This is what we get out from that. So in a sense, this isn't anything that insightful, but yet it is. Yet even then, it's some of the most interesting physics that there is. So the first law heat is a form of energy. So I'm going to first ask you to discuss amongst yourselves why you think heat is a form of energy. We learned about like potential energy, kinetic energy in class already. Why do you think heat is a form of energy? Just discuss with your partner. While you guys are talking, please remember to fill out the attendance form. The word today is baby. Yalki.com/baby. Yeah.
My name is Priscilla. I am.
Yeah.
Yeah. I'm the not able to attend like this timing or.
Okay. Email us and we'll work it out.
Okay. Yeah, but starting today, like I can see.
Okay.
Around consistent.
Okay.
Cool. You guys know.
Okay. Thank you.
Yeah.
What did you guys come up with? What did you guys come up with?
I was just thinking that it requires energy for a particle to move. The more it moves, the more hot that general area becomes. So maybe energy is required for things to be hot.
Mm-hmm. Yeah, that's definitely one way to look at it. What about what is the relationship between heat and how fast something is moving? Like,
Well, I was going to say that can be considered since it's a form of energy, can be able to create enormous rocks.
yeah, that's also true.
Things that are hotter or like they have more kinetic energy.
Yeah. So basically, like heat is roughly the amount of kinetic energy that each individual particle has. But don't like, this is not mathematically rigorous, but it's a good way to think about it. It's basically the amount of kinetic energy that individual particles have. But this is like very, very interesting. This means that heat, again, I'm going to keep bringing this up throughout the lecture, but heat is like an emergent property. We don't know the specific velocities of each individual particle in this box, but yet something called heat is something we can measure, usually, at least heat transfer. And we don't need to know the velocity of each individual particle to touch a stub and feel that, yeah, that's hot, right? So that's something that emerges out of, even despite us not knowing the individual energy. And she sort of preempted me on this one, but energy is always conserved. So that's the second part of the first law of thermodynamics. Second law, and you already know this. This is true from Noether's theorem, but it also applies to heat. So you can convert work, which is like your classic idea of energy, into heat, and vice versa. And the total energy must be conserved. Yeah. So this is the big one, the second law of thermodynamics. In my opinion, possibly the most important law in certainly thermodynamics, maybe even physics. Okay. So entropy. This is something which, when I initially learned about entropy, it seemed like this really, really vague and abstract concept. And it didn't seem like something that was like very real. And when in the 1800s, scientists, physicists, statisticians were learning about systems like gases and stuff, they basically were doing some math, and there was a number that was coming out of the math. And they called this number entropy. And this seems like it's just a number coming out of the math. But it was also very much like a real quantity of a thing. It was very much like an actual thing, like say mass. If I have mass and I double the size of an object, the mass also doubles. Entropy was the same. If you have like an object, you can calculate a number for it, which is called entropy. And if you double the size of this object, the entropy also increases proportionally. So it seems like a thing that you can assign to an object or a system. So you can sort of think of it maybe and initially people sort of thought of it as something like a fluid or something like that. But they didn't really know exactly what it was. And what I can tell you is, again, entropy is something just like heat that is an emergent property of a system. Let's say, and one way to think about it is like the number of ways to arrange a system. Let's take a really simplified example of like a gas in a box, which is a deck of cards, right? In a deck of cards, there are 52 cards. How many ways are there to arrange a deck of cards such that all the cards are in ascending order and sorted by suit? There's one way. There's only one way to arrange a system where they're all in order. Why? So okay, we have that. How many ways are there to arrange a card deck such that all the cards are in order and in the right suit, except the aces are all in the front, and that's all we know. We just know the aces are in the front. We don't care about their suit. Well, 4, right? Because the aces could be in any order, right? But all the cards after that are in order, right? Now, how many ways are there to arrange the cards such that they're just completely shuffled?
52 factorial.
Yeah. Okay. Well, I didn't really expect you guys to know that, but it's a very large number. So 52 factorial is a mind-blowingly large number. It's like it would take me a lot of time to write it down, so I'm not going to write the actual number out. But it's a very, very large number. But this could apply to velocities as well. Like how many ways are there to arrange energies or velocities in a box? But in this case, it's like the number of ways to arrange the system is one way to look at entropy. Another way to look at entropy is, well, how much do we know about the system? How much information do we have? How much do we care about as well? So like, if you have a deck of cards in order, you know that there's only one way that can happen, right? And you care about the deck of cards only if it's in that specific state. If you have the aces in the front, but you don't care about the order of the aces, then you don't care about it as long as the aces are in the front. And so you don't know which order the aces are in. And if you have a shuffled deck of cards, you don't know anything about it, right? You know nothing. So another way to look at this is, I don't know, how many of you are like CS or CS related majors? Have you ever seen or heard about image compression? Like the idea is, if I have an image, it's made out of a bunch of pixels, right? And let's say I want to compress the size of this image so I can send it to someone else, right? and I want to compress the size of the image as far as I can, right? So let's say I have an image of this room. Well, there's a lot of white in this room. If I take a picture of this room, adjacent pixels are likely to have the same color, right? And I can sort of describe the image and compress the image by saying, okay, the pixels in this region of my image have the same color, and that compresses it somewhat, right? If I take a picture of like complete randomness, there's no way, like pixels next to each other have no correlation. There's no way I can compress that image down. And let's take the case of like just a picture that's of like a completely blue wall. Every image, every pixel adjacent to each other has exactly the same information. So I can just describe this image to you in one sentence. It's a blue picture, right? And so the amount of information I need to give you an idea of that picture is the amount of entropy, right? And the minimal entropy state, the state with the lowest entropy, is where I can describe it with the least amount of information. For instance, the blue wall, I just need one sentence to describe it to you. Whereas for higher entropy things, I need more information to describe it to you. And this seems, again, like a very vague and abstract concept, but it's something that's very rigorous, mathematically rigorous. And the second law of thermo, and so I'm obviously belaboring this, but I think this is really, really, this is one of the coolest parts about thermodynamics, entropy, and the idea of like the number of ways to arrange a system. And the second law of thermodynamics basically says entropy in a closed system must always increase. So let's leave that aside for 1 second. And I'll come back to that. The third law says that, let's say I take a system. Again, you can think of your picture, like a picture of a wall or something. As entropy approaches 0, temperature approaches a certain number. Does anybody find that weird? What does that actually mean? When entropy approaches 0, that means when I can describe the system with almost no information at all. I just need to tell you that everything is completely at standstill. The temperature approaches a certain number. And in Celsius, this is some completely arbitrary number, minus 273 degrees Celsius. Why do you guys think that is? I guess you can discuss that. What did you guys, I heard you guys talking about Kelvin. What did you guys think? Why is it that as entropy approaches zero, temperature approaches like a number.
I'm not sure why, but we label 0 Kelvin as negative 273 Celsius. So like that's kind of correlation. We don't know why it's like that.
The foundation of Kelvin is that something like it's not moving at all, like or something like this. So I have like this vague memory of learning that. And so you can imagine that as entropy approaches zero, as something is coming to a complete standstill, there is only like a certain temperature that you can get to.
Yeah. Yeah, that's I asked this as almost a rhetorical question. Like the other way I could say it is like it's really interesting that like as entropy approaches zero, the temperature doesn't just keep reducing as you get closer to zero entropy. It actually approaches a number. And in Kelvin, like if you know anything about the Kelvin scale, we call this number 0 Kelvin. But this is like sort of the same as how we call 0 degrees Celsius the freezing point of water. It's kind of arbitrary, and we just set the Kelvin scale at 0 based on that. But yeah, it is really interesting that the temperature actually approaches a number. And basically, what this means is, as I can describe a system, an object, to you with less and less information, that the temperature is actually getting closer and closer to a certain number below which, and that number which you can't actually reach. So you can't reach a 0 entropy state. And well, lastly, they added the 0th law of thermodynamics. This is kind of like Python, I guess, which is sort of the transitive property of what do I mean by that? I mean, transitive property is like you learned about this in geometry. I don't know where you learned it, but it's like if one thing and one thing are equal, and something else is equal to that, then all three of those things are equal to each other. This is the same. If two objects are in thermal equilibrium with each other, and you have a third object, that third object is in thermal equilibrium with one of your objects, then it's also in thermal equilibrium with all three of the objects, basically. So, and basically, one way I've heard these three laws summarized is, well, there is a game. You can only break even. You can't really break even. And you have to play. You have to play because if you can't ever reach zero entropy or absolute zero, then you're always stuck at positive or at least at non-zero temperature. So you basically have to have some amount of entropy. Yeah? Do you have a question?
Is there like a theoretical maximum entropy?
Yes. There is a maximum entropy, yes. Well, of any one closed system. The maximum entropy is when you don't know anything about the system at all. For a deck of cards, if it's completely shuffled, the maximum entropy is a completely shuffled deck of cards, right? Because you don't know anything about the ordering of the cards at all. And that maximum entropy state exists for pretty much any system. But there is, as far as I know, there's no maximum temperature for any system. And I have to think about that. But yes, there is a maximum entropy for every system. And that's when you know the least information. So you can never be at 0 Kelvin. So you have to play the game. Heat is a form of energy, and energy is conserved, which means you can only ever, like, you can't lose energy by doing anything. So you can only break even. And possibly the most important law, you can't actually break even. Entropy in a closed system must always increase. So I want to come back to this. And basically ask you again, why do you think it must increase? Why, what idea do you have for why entropy increases? Why doesn't it just stay constant? Why isn't it, for instance, conserved, like heat? Heat is another emergent property of systems, like entropy. Why is it that entropy is increasing, whereas heat is conserved if you can't work? Maybe discuss.
But like, yeah, why would why would we eventually reach that factorial?
You can get us close. In fact, in like labs, I've seen things at millikelvin. That's
Like 52 factorial
really, really
accounts for
small
all of the possible things that you get.
I wonder.
This is a good question.
And
Are you asking like instrumentally, like in real life,
Yeah,
so you
that's
actually
right.
measure?
so that's
Theoretically, it can give you the answer, which is you have to figure out how fast the particles are moving in that system. And so if you like use a laser, for instance, to cool down your system,
I don't know.
to where and you use a laser to cool it down where you know that the particles are moving like at so and so, each particle has so and so kinetic energy. Then you know that
No, but it's like an interdisciplinary.
all right.
So the entropy stuff, like the system changes. First it's the A6 and then
So what did you guys come up with? Why do you think entropy increases? Do you guys have any ideas? No idea.
Disorder's favor, like going into a state of like chaos.
Yeah, that's a really good way to put it. Yeah.
Would it also be due to the fact that the universe is constantly expanding, so then it increases the non-disorder?
Even if the universe weren't expanding, the entropy would still increase. In fact, I've said here, entropy in a closed system must always increase. Even if my universe was a box, and the box like started up. Okay, I don't want to give this away, but even if the universe was in a closed box, the entropy would still increase, making a crucial assumption. But yeah.
Is it because of always uneven distribution of energy? Then energy will always flow to a state of like less of energy?
Why is there an uneven distribution of energy?
Because like stars radiate energy and stuff like that.
This is a very deep question, and it actually the real reason. So he's right. Entropy in a closed system increases because higher entropy is favored in a sense. If I have a deck of cards and I have it completely ordered, that means I know that it's in order, and I only care about it if it's in order. And now I throw the cards up in the air. Now I don't know anything about the order of the cards. Suddenly the entropy of these cards has increased a lot, right? Yeah.
But why is disorder favored rather than order?
And that's it's a good question. Maybe they have spins. Maybe they have like So there are only a few things that defines the state of a system, right? And when I say state of a system, I mean every property that I could assign to an individual particle. And because of this, I can define entropy rigorously. It's not subjective. When I say order and I say disorder, that's like statistics here. But again, remember that a higher entropy state is defined as like something where I know less, right? Does that make sense? All right. If you have a better explanation of this, Nicholas or Shishir, you can jump in. Yeah.
So with the deck of cards, I mean, it has the maximum entropy of 52 factorial because us humans have decided that a deck of cards is 52.
Yeah.
And so that's what makes it objective. Is that what you're saying? Because, all right, here's this number and here's the maximum entropy you can get.
So
Yeah, in a sense.
One common misconception people have is that like a shuffled deck of cards has like a lot of entropy or something. This is not necessarily true. If I told you like where every single card was placed in this deck, and you knew that information, then it would have no entropy. Right? But if I just told you I have a shuffled deck of cards, you know literally nothing about it, which means that it has the maximum entropy it could have. This
could be even more confusing, and maybe this analogy isn't the best analogy, but the reason I give it to you is because, again, entropy is the amount of information we have, right? If we have a shuffled deck of cards, the maximum entropy part comes from the fact that we don't actually know what order the cards are in. If you tell me that the cards are in the order 5 of hearts, 7 of spades, 3, and like you tell me the order of the entire deck, and you say, I only care about the deck if it's in that order, suddenly that specific configuration has very low entropy. The high entropy comes from the fact that we don't know or we don't care what the specific arrangement is, right?
Yeah. So if you have a deck of cards and you shuffle it, it has like the maximum entropy. But then if you tell me what the configuration of the cards in that deck is, that entropy then, the deck of cards then has 0 entropy, and that entropy gets transferred to my brain, if you want to think about it that way. But that's literally how it works, because that's how the information.
So we're not going to explain Maxwell's demon, I think.
I could explain Maxwell's demon.
But that's the resolution.
Should I explain Maxwell's demon?
Yeah, can you do that?
Okay. So Maxwell's demon is this like hypothetical experiment where you have like, and again, Nicholas, I'm doing this on the fly, so correct me if I'm wrong. I have a box with a gas. Actually, I'm just going to use that box. Why not? So this is a box with a gas with a bunch of particles in it. And I partition this box, and I put another box here. Okay? And I have a door in the box. And we have Maxwell's demon here. And he is going to open the box. Wait, Nicholas, so is there a specific like configuration at which he opens the box?
Yeah, for hot particles.
For particles above a certain velocity?
You're right.
Right? Okay.
So to let hot particles go to the left.
Yeah, so basically he only opens the box if the particle is coming towards him at above a certain energy, right, or velocity. And if it has any energy below that, he closes the box and he doesn't allow it to go in. Eventually, you have a box at a certain temperature T. Let's say that's like, I don't know, 10 degrees Celsius, just to put a number on it. And let's take away the demon for a second and let's just have an opening, right? You know from maybe chemistry, or if you don't know, then, well, now you know that if you just left the door open, eventually the particles would diffuse all around this box, and the temperatures of both of these boxes would be equal, right? But now we have Maxwell's demon here. And he's opening the box only if the particle velocity is above a certain number, and closing it if it's not. Eventually, with Maxwell's demon, we are going to get one box that's at a higher temperature. This box will have a bunch of particles moving really fast, let's say 100 Celsius, and this box with a much, which now has only the particles at low temperatures. So now we have a temperature gradient between these two boxes. You can use this to do work. You can put a generator here or something. This box is hotter than this box. And you can have heat transferring, and you can drive an engine with this. And where did this energy come from? Right?
Discuss.
Yeah, like
Trying to figure out what is the solution to this. Where does that energy come from? Why is this not a violation of those laws listed that we have there? Especially, you can only break even, or and 2 entropy in a closed system, so 1 and 2.
I know that they're opening a door and they're molecules in, right? Does that mean that does that mean that in the first place? So the molecules were
does anybody have any idea? Maybe the idea, like I don't know if any of you had this idea, but let me just
Like where the energy is coming from?
yeah.
Is the demon itself
Opening and closing the box. That's what I thought. When I learned about Maxwell's demon, I was like, okay, surely it takes energy to open and close the box. It doesn't though, because like you're opening and closing a box. Like it takes a minuscule amount of energy just to open and close a door. That doesn't end up adding to the actual amount of energy. And like let me put it this way: Maxwell's demon can decide that only for particles above a kinetic energy of 10 joules will I open the door. This is a completely unrealistic number, sorry. And this takes a certain amount of energy to open and close the door. Maxwell's demon can also decide I only want to open and close the door for particles above 100 joules. Only difference there is the temperature, but the amount of energy it takes to open and close the door is the same. In fact, it's even less because you have fewer particles at 100 joules. So this doesn't add up. This actually is not the reason. Opening and closing the door is not the reason.
Like, you treat both boxes as a separate system almost, and then when the particle leaves the system on the left, there's like this change in heat that gets like converted to energy, and then same for the other box, like when it enters it.
What do you mean it gets converted to energy?
Like, because energy is always conserved, so like when that box like loses heat,
Yes.
it must generate like some other form of energy.
What other form of energy is that?
Like whatever type of energy you're like, talking about.
Well, kind of. Not really, I would say. Yeah?
Maybe because like from the outside you know the temperature, and that's like you kind of like knowledge that you have. It's kind
of like that's the real reason. As mind blowing as it is, Maxwell's demon is hypothetical, and the reason why Maxwell's demon is interesting is because we've constructed this hypothetical case in which Maxwell's demon is all-knowing. He knows the velocity of every individual particle. But the initial basic assumption of thermodynamics is that we don't know the velocity of every individual particle. If Maxwell's demon is sitting here and he knows the individual velocity of every single particle, the system is at zero entropy. Basically, the energy gradient that the heat gradient that Maxwell's demon is creating comes out of his knowledge about the system, and nothing else, right? Another way to say that is you can't know everything about the system unless you put in energy to gain that information. that's where the energy conservation comes in.
So this is, in my opinion, this is a really, really cool link between energy and information.
Yes.
And this might come up later in the course as well. I think this is really, really cool.
Yeah. So yeah, Maxwell's demon, this is possibly the one hypothetical experiment where, again, just like the twin paradox, just like a lot of other things in this course, we've constructed this hypothetical example, and we haven't really told you the one sort of assumption that we're making here, which is that Maxwell's demon is all-knowing. And that assumption is what unwinds this story. And in order to be all-knowing, you also must have a lot of energy. Information is very, very closely linked to energy, and information is also closely linked to entropy. So, in a sense, in order to gain information about each particle's velocity, you need to put in energy to get that information.
Right. So yeah, the idea is more when you take away entropy from the system, it's like going into your head, right? Like your head stores this information, right?
And therefore, your head's entropy increases proportionally.
Wait, so you're saying that because he knows every particle, the entropy approaches zero. So you're basically saying if we know more about a system, the temperature of that system is gonna approach. But how does that not?
Well, see, the thing is, in this case, Maxwell's demon is part of the system. He's changing the system.
Oh.
His brain, this is getting philosophical, but let's not get into the philosophy of what it means to actually know something. You can think of information as bits, right, stored in a computer. You can think of information as stored in bits on a computer, and there has to be some physical way of using that information to make a decision. And the laws of physics state that if Maxwell's demon is using information to make a decision on whether to open and close the door, then that entropy must be going on, that entropy must be increasing in his storage of the information.
On this week's problem set, you will encounter an example of the highest entropy could possibly be, and just bear in mind that if your brain had that much entropy, it would become this.
I think you gave away too much there.
It's fine.
Yeah.
So are you saying that there is second maximum entropy
Yes,
of our universe?
there is. And,
Yes.
and we don't want to give away too much, but you'll do it on the problem set. It's a cool problem.
Okay. So this is let me check my chart. Okay. This is very cool. But I have to move on from it. Yeah?
If there's a maximum entropy of the entire universe, does that mean if we could have all of the information to know everything about the universe, then the universe is just determined? Would that give rise to determinism?
This is a philosophical
This is a really good question.
It will not be answered.
I can't. Yeah. So come to us after class, and I'll try to answer that. But that's a really, really good question. One more comment I want to make about the fact that entropy in a closed system must always increase. What does that mean? So far, we've learned about space and time and special relativity. We've learned the definition of time. We learned why time is different from spatial dimensions. Nothing we have learned in physics has done anything to say that if I take a video of the universe from its start and then I rewind that video, that I'll be able to tell that there's a difference.
Physics doesn't change.
Physics doesn't change. I can take a video of the universe from its start until now, and I rewind that video, you will be able to tell that there is a difference. Subjectively, in my physics textbook, which I never understood, the way they explained this was saying, oh, there's a wine glass, and the wine glass falls and shatters. On a video, how can you tell that the wine glass like, how can you tell if you took a video of that wine glass falling and shattering that, that it was played in forward versus played in reverse? But you can tell, right? You can tell. This is the subjective way to say it, but there's a rigorous way to say it as well. Thermodynamics is where we get the arrow of time. And this is like a huge, this is why thermodynamics, like it starts off, oh, it's like just a box with gas in it, but then it actually like it becomes, there's an arrow, like time has a direction. And mind you, nothing we have done so far is anything different from classical mechanics, right? Like literally we could just know your half mv squared and like maybe the rest of classical mechanics, and you'd be able to do all of this. This is just statistics for when you don't know things. And out of that, you get two things. One is that time has a specific direction, and secondly, that in order for entropy in a closed system to increase over time, including the universe, that means entropy must have been lower, and it's getting higher. So why wasn't it high to begin with? This means that the universe started off in a really low entropy state, and it's getting higher. So just based on statistics, we've come up with the fact that the universe started in a low entropy state, and the entropy of the universe is getting higher. This is mind-blowing. And now we're into cosmology, so we'll explain that hopefully later. But I'm just going to write down. Question.
Is this why there's a minus sign in the metric?
No. Even though there's the minus sign in the metric means that time is different from the spatial direction, right? But you can still reverse time and like let's say the universe was a box and the particles in that box were just like uniformly like moving randomly. Nothing would ever evolve. The universe could have been like this.
Let's put it this way, like you can think of the metric that we talked about as like being related to like the laws of physics, but if you took t and you replaced that with minus t, it would still be the same equation.
Yeah.
The equations that we have dealt with do not know what direction time is.
Yeah.
So how
They don't
do we
specify a
know?
direction for time, right? Like the metric specifies you can plug in a value for time, right? But it doesn't specify that time goes in a specific direction. It just, in practice, we observe that it happens to behave this way.
And furthermore, no actual law of physics specifies a direction. In some sense, it's a law of statistics. It's just the way statistics works, that if I take a deck of cards and I throw it into the air, it's like the entropy in that deck of cards will increase, right? But that means if the universe started off with gas in completely random directions, no completely uniform, no pockets of density, then that means nothing in the universe would ever have evolved. The fact that we have galaxies, the fact that we have stars, the fact that we have planets, the fact that we have humans is all the result of the fact that the universe started off at low entropy and is inexorably getting towards higher entropy. So this is really, really interesting. But I will move on. So I'm going to say entropy increasing means time has an arrow. Now I'm going to talk about something that seems very different, but it's also again like in the theme of things. Let's see how much time I have. 30 minutes. Things basically emerging out of us not knowing things about a system, and this is degenerate matter. Degenerate matter, you think you've never seen degenerate matter. Let me first explain. This is going to kind of overlap with with quantum and particle physics, but we'll see. So a boson, I'm just going to tell you, a boson is a type of particle. Okay, and that is what it is. It's a type of particle and an example of a boson is a photon. Okay, that's just one example of many. You might have heard of the Higgs boson, that's another boson. And bosons behave in a very generic way. Like, they're sort of like generic particles. But let's say you cool a boson down low enough. You take a bunch of bosons and you just like reduce the temperature so that fluctuations, like random changes in temperature, are also very, very, very low. That just random changes in temperature are very low. I'm going to tell you one thing about quantum mechanics in this lecture, and that is, in this case, if you reduce temperature fluctuations so that they're really, really low, that means the energy of the system, the heat energy of the system, is very low. And what I'm going to tell you about the quantum mechanics is that it's like the world is made out of pixels, okay? And specifically energy is like pixelated, you can think of it as. And normally in our everyday lives, we see the image. We don't see individual pixels. If we cool a system down, if we cool a bunch of bosons down so that the temperature fluctuations are really, really low, suddenly we start to see the individual pixels of temperature. Temperature and energy is quantized. How I'm going to demonstrate that is, normally temperature is pretty continuous. Like, I can take 53 degrees Celsius, 53.1 degrees Celsius. It seems very continuous. But if I have a bunch of bosons and I cool them down a lot, it becomes pixelated. So I'm going to draw energy. I've cooled down these bosons, and now they all settle into this lowest pixel of energy. This is called the ground state. Maybe there was like one boson here. Okay? I keep cooling the system down until almost all the bosons are at this lowest pixel of energy, this lowest quantization of energy, called the ground state. And if they need to move up, let's say I add like 0.001 joules of heat. This is, again, a completely arbitrary number. What will happen to these? Well, the problem is the energy is quantized. So unless I have enough energy to go up this ladder, these bosons will stay at the ground state. Like, I can actually add energy to these bosons, and I will not be able to raise them past the ground state. This is not intuitive. So I want to make sure this is very clear. Like, it's very, very intuitive for us to be able to add energy to something, add a small amount of energy, and it increases energy. If I increase the energy of these, they will not move up. Their energy will actually not increase. It's quantized. So, well, you can think of this as like life alert. Like, these bosons have, like, I've fallen and I can't get up. Was that dark? So these bosons cannot get up to the higher energy state. What happens when you get that? This is something called a Bose-Einstein Condensate. An example of a Bose-Einstein condensate is liquid helium. If you cool helium low enough, you basically have a bunch of bosons at the ground state, and really, really cool things happen if you have a macroscopically large number of bosons at the ground state. What was that?
Haha, cool things.
So for instance, let's say I take liquid helium and I stir it. This is what happens. You start getting these like symmetric vortices that come out. There was a really cool video of this which I can't find. But another cool thing about Bose-Einstein condensates, they don't have any viscosity. Liquid helium, which is a Bose-Einstein condensate. If it's a Bose-Einstein condensate,
It has to be cold enough, not
yes,
all
yes,
liquid.
yes, yes. If liquid helium is a Bose-Einstein condensate, it's not like thick, like a fluid. You know, like honey is thick, molasses is thick, water is less thick. That's viscosity. Viscosity is how like thick the fluid is. Yeah.
So if I put my finger in it and didn't get it like frozen off, you feel like I'm putting my finger into nothing? Like air?
Yeah.
It would
Like
flow up your
even
finger
less
if I'm
than
not
air.
wrong.
So, no one's ever tried that.
For obvious reasons.
What happens is this kind of fluid actually will flow up walls, like, interestingly.
I don't think its behavior
So
is
like flow
particularly.
up my finger?
Yeah.
Yeah.
It flows up the
How
sides of
far
its
up?
container, so you need a
Oh,
special.
it will just climb up any surface that it's in contact with. So in order to store it, you need to put it in like a closed container, otherwise it will crawl out.
Basically,
It sounds like a joke, but it's not.
crazy stuff happens. Like Bose-Einstein, this is why like if you take a system and you bring all the particles down to the ground state, specifically bosons to the ground state, you're actually like, this is quantization of energy, right? This is not something you experience in your everyday life, the pixelation of energies. In everyday life, energies just look continuous. But if you do make pixelation of energies an important thing, really unintuitive, weird stuff happens. And that's an example of that is a Bose-Einstein condensate. Yeah?
But if you open the container of the liquid helium, I mean, wouldn't the energy in the room interact with the liquid helium? Like it wouldn't just stay in that state.
Yes, that's absolutely correct. So we're like, nothing of this violates physics, right? Like energy is still conserved. Only if the system stays as a Bose-Einstein condensate. If you give enough energy for these bosons to get up off the ground state and go up, then it just behaves normally. But we're assuming that we're keeping this cold enough and keeping temperature fluctuations low enough to keep it at the ground state, right? So,
Question?
And specifically, by the way, degenerate matter refers to like the next phenomenon.
yeah, so I'm not at degenerate matter yet. This is, yeah.
So helium isn't a boson, right? It just
Oh,
acts like it,
That's
right?
that's a good point. Helium's nucleus is a boson, and over like the scale of the helium atom, it behaves like a boson because the nucleus is like most of the helium atom. So like overall, you can consider atoms as basically bosons. And so they're
well,
behavior.
it depends on the atom.
Yeah, but the behavior closely for helium, the behavior closely parallels a boson.
And just to preempt this, helium-3, like if you have like the kind of helium which is 2 protons and 1 neutron, turns out to actually not be a boson, but we will not explain why.
So, yeah, I don't want to go into spin, but like, yeah, bosons are a specific type of particle for the purposes
I think
of
we
this
can
class.
cover that in
Not-
conversation.
Yeah, we will talk about it, but not today.
Yeah.
So there's another type of particle, and like, okay, I talked about bosons. Now I have to set up the foil. Fermions. Another type of particle.
I think you should add like.
Example. Electron. Neutron. Electrons and neutrons are both fermions. There is something very interesting about fermions that's not true about bosons. And I, as of now, do not have a very good intuition of why this is the case, but it's almost white hot. If I cool it down, I get near infrared to the temperature of a warming stuff. And if I cool it down even further, humans are not, oh, my battery died. So humans are even cooler than a stuff, right? And humans also glow in far infrared. If you were to cool yourself down even further, you would glow in even further wavelengths. So the basic idea of black bodies is that let's take any object and let's just ignore the fact that objects reflect light, and let's ignore the fact that objects absorb light. Let's just say objects are essentially black, and if you do this, all objects glow at a certain, and so the wavelength lambda, if you increase the temperature of an object, the wavelength goes down. That's what that equation is saying. So you make a temperature hotter, the wavelength gets squished of the light that it's emitting, of what wavelength it's glowing in. All right. That's basically black bodies. Do I have time to explain fluids?
You don't need to. I think we can cover that later.
I just want to explain two things about fluids. So fluids, this is a pretty crammed lecture, isn't it? Fluids. The one thing I want to explain about fluids is there are two regimes. If you have water that's flowing, it can. Okay. Let me first say the basic idea of fluids, and the reason why we're explaining it in this lecture is because it is basically statistical mechanics, except in a gas, you have particles moving around and they're not interacting with each other at all. They're just sort of moving. In a fluid, your particles are actually feeling forces due to each other. And so it's basically statistical mechanics in the limit of lots of interactions, of significant interparticle interactions. And so if you have a liquid, and that's the definition of a liquid, lots of interparticle interactions, and you sort of just let it flow, it could flow laminar, which is just like smooth flow, or it could be turbulent, right? Which is like this is turbulent flow. If you've ever been in an airplane, you've probably experienced turbulence. That means there's choppy or not very clear airflow over a wing. All I want to say before you guys go is that turbulence is the result of vortices, which are little worlds. So there's this poem, which is the quote of the day. Big worlds have little worlds which feed on their velocity, and little worlds have lesser worlds, and so on to viscosity. What that means is, if I break down this messy, flowing liquid, what I will actually see is that there are little worlds. And in turbulent flow, if I zoom in on a world, it'll be made of smaller worlds. And it'll be made of smaller worlds until a certain point. What does this kind of remind you of? Talk amongst yourselves. And I'll end the lecture there for today.